In this lesson, we shall focus on physics. Physical sciences 2024 June past examination question paper, and we shall start off with question 2. A block or block A of mass 4.1 kilograms is connected to block B. Right, we can see block A there is connected to block B of mass 2.3 kilograms by a light inextensible string passing over a frictionless pulley. There is the pulley, frictionless there. Block A is at rest on a rough horizontal table. And right, so now this is very, very important. To start off with, block A is at rest. So its velocity initially is 0, but it's also on a rough horizontal table. And the block B hangs vertically as shown in the diagram. The fact that this table is rough, it's indicative of the fact that there is a friction there. Right, a force F of magnitude 49, magnitude 49 newtons is applied right on block A at an angle of 50 degrees. We're able to see the force of 49 newtons and at an angle of 50 degrees there. Okay, let us continue and analyze the rest of the paper. Right, and this angle of 50 degrees is to the horizontal. This is to the horizontal, causing block A to accelerate to the left from rest along the table. It's accelerating to the left. To the left from rest along the table. The coefficient of kinetic friction between the surface of the table and the block A is 0.35. Okay, they've given us, because it is rough, there is friction between the block A and the table, and so the coefficient of kinetic friction between the surface of the table and the block A is 0.35 there. Dimensionless unit quantity. Okay, right, we're good. We're so good. State Newton's second law of motion in words. Right, and now obviously we need to start practicing the laws. Right. Right. We continue. We continue. Okay, yeah, we start with the law. Okay, so try to always stick to the laws now. This is the 11th hour. You don't need to learn them the day before. Right, when a resultant force, you just note all the words. When a resultant force, right, acts on an object, right, on an object, the object, comma, when it acts on an object, comma, the object will accelerate, in the direction, of the force. The acceleration is directly. The acceleration is directly. Right. We've put a full stop there. Then we then say the acceleration is directly proportional to the resultant force. And inversely, proportional to the mass of the object. To the mass of the object. Right, so we are here. When a resultant force acts on an object, the object will accelerate in the direction of the force, full stop. The acceleration is directly proportional to the resultant force and inversely proportional to the mass of the object. We repeat again. When a resultant force acts on an object, comma, the object will accelerate in the direction of the force, full stop. The acceleration is directly proportional to the resultant force and inversely proportional to the mass of the object. This is how you must state the law for 2 marks. It's already there on Friday. This one is already there. Because this one, they can't change it. What can they change? They're going to change the numbers in the question, but the law is going to be there. It's going to be there. Why? Because this is about Newton's second law. And they need to ask Newton's second law there. Okay, they need to ask about it. Right, so we note that one. 2.2. Draw a labeled free body diagram showing all the forces acting on block A when it accelerates to the left. Block A when it accelerates to the left. So we have block A, and now we are able to identify force F that acts on block A. Simultaneously, there is a normal force that is directly upwards, which is the force by the surface on the block, pushing it directly up. There, a normal force. We have already our weight that is straight down. We have the tension in the inextensible string, and the tension is T. We also have the fact that the applied force is to the left. Therefore, we have what we call the frictional force. We show by lowercase symbol f over there. Right, and therefore, this is the free body diagram there. So now we have drawn the free body diagram because the block has a weight W, a normal force N, a tension T, an applied force F, the friction lowercase f. Lowercase f. Lowercase f. Okay. All right, good. Let's look at the next one. We're looking at the next question. Right now, we want to do a calculation. Right, we need to calculate the magnitude of the kinetic friction force exerted on block A. The magnitude of the kinetic friction force exerted on block A. What formula are we going to use there now? Think about that question for 3 minutes. Think about that question for 3 minutes. The magnitude, not direction, but the magnitude of the kinetic friction force exerted on A. Exerted on A. Right. Exerted on A. Right. All right. Okay, let's do it together. So, but first we'll note that the kinetic friction force, I noted your answer is 14.06. So it is actually this, and we write F normal force. You can write N or you can write F normal. But you see, as we have studied here, we have this one. We have the applied force. We have the tension. Okay, yes, please try it again. Let me give you a chance. I'm giving you a chance to try it again. Because we're practicing here. We're preparing for Friday. So we want to make sure that we iron out like everything. Right. We need to make sure we iron out everything. We need to make sure we iron out everything. We need to iron out everything. Right. Please let us know when you're done because we're practicing. We're not running. It's not a marathon. The marathon is going to be on Friday in the exam. But we're practicing here. All right. 0.92 is okay. 0.90 is okay. So obviously now we need to do a couple of things because now when we look at these, then this is going to have the fx, fy. The fx, fy together will be the horizontal and vertical components of the applied force. Right, so then you're going to deal with the Fy, F normal, and the weight. Those are the vertical forces. Because there is no motion vertically, it then means that you're going to have the F normal in the same direction as Fy, it must be equal to the weight. Must be equal to the weight. But now, sometimes the weight is called Fg. It's called Fg. So it means that in this case, you have the normal force together with the vertical component of the applied force, and then it must be equal to the gravitational force because there's no vertical displacement there. So in the end, this is what we have. So we'll then come here and then say Fk would be mu k. The Fn is going to be Fg minus Fy. Because obviously we agree that we have the 1, 2, 3 forces in the vertical direction. Okay. So now with this, we then say Fk is equal to the mu k, the coefficient of kinetic friction between the surface of the table and the block is 0.35. So we have 0.35. This one is mgfy. Right. Which means Fk. What is the mu k? 0.35. The mass of the block is 4.1 kilograms. They're 4.1 kilograms. 9.8. Can write 9.8 minus this component, the vertical component is the sine. Right, so obviously this one is mu k, mg, and this is f sine theta. Right, so it's minus the applied force 49 newtons. The sine of 50 degrees. Right, so let's use our calculator here to see what we're getting. Check it out. Right, so we check it out. Right, so what we're going to have is 0.35, open bracket, 4.1 times 9.8 minus 49 times the sine of 50. Which is 0.925. 0.925. Yep, we can approximate it to 0.93 newtons. Obviously, this is correct. In the exam, they're going to accept 0.92 to 0.93. Yeah, that is what we have. That is what we have there. And so this one here is actually the answer to this question. We've calculated the kinetic friction force exerted on block A. We've calculated the kinetic friction force exerted on block A. Right. Kinetic friction force exerted on block A. We calculated the kinetic friction force exerted on block A. Right, so we're good. Yup. Okay, I'm glad then. Then we move on. Okay, good. We try the next question. Calculate the magnitude of the acceleration of block A by applying Newton's second law to each block separately. Let us find the acceleration of block A for 5 marks. I'm giving you 5 minutes to try that one, then we discuss it together. Right. I'm giving you 5 minutes. Right. So we continue. We continue. Right. We continue. We continue. We have 5 minutes to calculate the acceleration of block A. Right. Right. You have 5 minutes. You have 5 minutes. So as soon as you're done, please let us know. You chill. Don't break your fingers. Take your time. We have the whole week to do this paper. So we shall finish it, of course. Even tomorrow we're meeting. The day after, you know. Not only this paper will be done, but also other papers as well. So please let us know when you're done. We continue. Right. We continue. Right, once you're done, don't break your fingers, please. We continue. Okay, y'all, 1.26. Let us obviously check together. We're going to work it out and check what we're getting. But obviously, always I put down your answers. So you're then saying the acceleration, A, is 1.26. I mean, you're suggesting that. So meters per second squared becomes acceleration. I said already, we're going to check it out. Now, the couple of things that obviously are actually very important here. So we must say for A, or for block A. Right, so this is for block A. On this block, F net is MA. So now you're going to have a couple of forces. If this is Fx and that becomes like Fy. So which means that we're going to have, for instance, our net force horizontally is going to be our Fx. The tension goes in the opposite, but also friction is in the opposite. And this is MA. Fx would therefore be F cosine theta minus T mu K Fn equals MA. Cosine 50. Now, we've already got mu KFN. We got 0.93 for this one, which is the force of kinetic friction. The mass of block A is 4.1 kilograms. It is multiplied by the acceleration A. Which means T is equal to what? Let us use a calculator to get the answer. Right, let's just use a calculator to get the answer. So we can then say, move T to the right-hand side, getting 0.9 cosine 50 minus 0.93. Right. Which is 49. $50. Which is 31.49659 minus 0.93 Right, and then you get the answer, which is exactly 30.57. 30.57 minus 4,1a. 30.57 minus 4,1a. Question 1. Next. This is actually obviously for block A. For block B, F net is MA. Obviously, for block B, we actually can acknowledge that we would have basically two forces, the force of gravity together with the tension. But because of the fact that we understand the system is sort of accelerating upwards because of the applied force, the tension is more powerful than the weight of block B, meaning to have tension minus Fg, which is equal to Ma. Tension minus Mg equals Ma. For block B, the mass is 2.3 kilograms multiplied by 9.8 of gravitational acceleration equals the mass. A. Which is 2.3A. Okay, then you're going to do 2.3 times 9.8. 2.3 times 9.8. Mm. 22.54. 22.54, and this would give us equation 2. Obviously, we agreed, therefore, that now equation 1 equals equation 2. Which means now 30.57 minus 4.1a is actually by dint of tension be equal to tension. 2.3a plus 22.54. So you bring this one to the other side now, it gives us 6.4, which is equal to now, yeah, we have that, 6.4. 30.57 minus 22.54. Minus which is 8.03. Right, so we have exactly 8.03. 8.03. As a consequence, what we're then able to achieve is that we can be able to get the acceleration. The acceleration is 8.03 divided by 6.4. Let's use a calculator for this. Right, it becomes 8.03. We divide by 6.4. And that is 1.2546. 1.25. 1.25 meters per second squared. Meters per second squared. 1.25 meters per second squared. Right, that is the acceleration of block A. So the acceleration of block A, obviously, you understand, therefore, that it is the acceleration of block A, as it said, block A to accelerate to the left. So this is the acceleration to the left. To the left. This is the acceleration to the left with that direction there. Right, so I believe that that is very clear and very easy. But this is what you're going to see on Friday, so get yourself ready then to understand more. They might remove the table and just put the thing on the ground. You know, they might remove the table and put the whole thing on the ground, etc. In which case, therefore, it will just be very similar to this one, and you will just obviously solve it in the same manner. Pay particular attention to a couple of tricks the examiners can play. But the trick that they played in the former question, what trick did they play in this question? The normal force here is not just equal to mg in magnitude, but the normal force is weight minus Fy. Fg minus Fy. That is the normal force because there's an applied force, so it's not just a normal force that is up. So note the trick in this question. Right, so as we move forward, we try the next one. Right, that was the very last question on the Newton's laws of motion, Newton's laws, yes, in particular the Newton's second law. We focus on the next question, but you see, the way we look at the next question becomes so important. Becomes so important. Becomes so important. Question 3, start on a new page. Okay, good. Right now, a hot air balloon moves vertically downwards at a constant velocity of 3,4 meters per second. Here is a hot air balloon and it moves vertically downwards at a constant velocity of 3,4 meters per second when the balloon is 15 meters above the ground. 15 meters above the ground, a small ball is dropped from the balloon. There it is, the small ball dropped from the balloon. Refer to the diagram below. Okay, the diagram is clear. We're able to see the small ball there that has been dropped. And now we attempt to answer questions that follow. The ball strikes the ground and bounces vertically upwards. Two things happen. It strikes the ground and then boom, it goes back up. It bounces, but vertically upwards. The hot air balloon continues to move downwards at the same constant velocity. This hot air balloon continues to move downwards. So it is not moving up, it just continues to move down. Ignore the effects of air friction acting on the ball. Define the term free fall. Define the term free fall. Okay, this one is too easy for 2 marks. Right, so free fall. Right. Is motion during which The only force acting is gravitational force. Is gravitational force. Free fall is motion, during which the only force acting is gravitational force. Free fall is motion, during which the only force acting is gravitational force. If you don't like this one, because this question is already there on Friday, free fall is motion under the influence under the influence of gravitational force only. Under the influence of gravitational force only. Free fall is motion under the influence of gravitational force only. Free fall is motion under the influence of gravitational force only. Okay, so we either define free fall in terms of red or the blue. Red is free fall, is motion during which the only force acting is gravitational force. So if something is falling and the only force acting is gravitational force or the weight, then we say the object is in free fall because there is no air resistance, there's nothing else. Free fall is motion under the influence of gravitational force only. So if the only force acting on an object that is in motion and the motion is actually such that it's under the influence of gravitational force only, this motion constitutes what we call free fall. This motion constitutes what we call free fall. Okay, obviously this is done for 2 marks. 2 marks. 2 marks. Okay, I know it's too easy, but yeah, I'm posing so that you can just try to internalize it. Let's move to the next question. These are the things you're going to meet on Friday. Try to understand. This is the message, like, try to understand. Try to understand. Question 3, you start on a new page, and that is the message in the physics class. In the physics exam, start on a new page. The sketch graph below, not drawn to scale, represents the positions of the ball relative to the ground from the time the ball is dropped until the time it reaches the maximum height. Okay, yeah, I want us to just pay particular attention to what is happening here. The sketch graph below, not drawn to scale, represents the positions of the ball relative to the ground. This is a position versus time graph. Position versus time graph. Right, but now it represents, this sketch graph below, not drawn to scale, represents the positions of the ball relative to the ground from the time the ball is dropped until the time it reaches its maximum height after the first bounce. Okay. Until it reaches its maximum height after the first bounce. But now, look. A couple of things are happening here. The ball is dropped. And initially, at time 0, the velocity is minus 15 meters per second. Or it's minus 15, the position. The position is minus 15 meters. Right, remember that the ball is dropped, so it's moving downwards. And because of this then, and the positions of the ball relative to the ground from the time the ball is dropped, its position was minus 15. This was the position. It was minus 15 from the time it was dropped. Minus 15 meters. Until the ball reaches its what? Its maximum height after the first bounce. You can see there's a bounce there because the position is like constant, and then it starts now moving again. But you're able to see therefore that as it moves in these cases, it moves from time 2 to time 3. And then it actually gets to reach its maximum height. But the way it bounces right now, you're able to see that obviously it actually does not reach the same position. Doesn't reach the same height from which it was dropped. So it reaches a lesser height. A lesser height. So this is very, very important. It reaches a lesser height. So I want us to understand this graph a little bit before we answer the questions. So from the moment it is dropped, the position is what? Is minus 15. And then it becomes minus 14, minus 13, minus 12, minus 10, blah, 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 until it reaches 0. It strikes the ground, and before it bounces, it's in contact with the surface for some time. It's in contact with the surface for some time. But you see, by the moment this ball moves all the way, its position is a negative position. It's a negative position. So if its position is negative position, and it is actually obviously on its way down, because it is dropped, it's moving, it is on its way down until it reaches the ground. It bounces. By the time it bounces, you are able to see a couple of things. That obviously its position begins changing again from 0. It begins changing once more. So these are the things you need to take into account. Was the ball in free fall between T1 and T2 seconds? Write down a yes or a no. I'll give you a chance. What do you think? What do you think? I know it's an obvious question, but yeah, what do you think? What do you think? What do you think? Okay, of course, it's a big no. Thank you so much. It's a big no. Because it was not moving at that time. So it was not in free fall. It was not falling at that time, but it was in contact with the surface. It was surely in contact with the what? With the surface. It was in contact with the surface. Right, we continue. Right, now this is still the same situation. Use equations of motion to calculate the value of T1 indicated on the graph for 3 marks. For 3 marks. For 3 marks. Right, for 3 marks. I'm giving it to you. Right, I'm giving it to you. Then you let us know what you think. Right. You let us know what you think. And then we shall do the corrections, of course. But yeah, always I must give you a chance to try the question and then suggest to me the answer. And then once you suggest to me the answer, then we can, yeah, can then do it together. I must give you a chance to practice. Practice makes perfect. 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 Please let us know when you're done. Please let us know when you're done. Right. Right. So remember, this question is from this one. Remember, it was from this one. So this, everything was moving at 3.4 meters per second. It was moving at 3.4 meters per second downwards with this balloon. Right. This hot air balloon. We are trying, please, we are practicing, so don't break your fingers, don't run, don't sweat, take your time and relax. We are here to try and understand what is happening. We're here to try and understand what is happening. Right. We're going to do the corrections, of course. We're going to do corrections, of course. But yeah, we're trying to test your skill a little bit. Every question we must try. Every question you must try. But I must give you a chance to try the questions, you know. We shall finish this paper. We shall do other papers also. Right. Shall do other papers also. Let's check it out. Let's check it out. Okay. 1.44 seconds, and I'm going to check if this is true. But to check if this is true. So now we choose downwards. Downwards is positive. Which is VI delta T plus half A delta T squared. Remember that the sketch graph below, not drawn to scale, represents the positions of the ball relative to the ground. So if we have the ground, and we choose downwards as positive, then the ball is released 15 meters. And then it goes down. And then it bounces and then goes up like this. But its position relative to the ground, we're measuring position from the ground to the ball. From the ground to the ball, we're measuring negative 15. From the ground to the ball, we measure the other one. Because we are measuring from the ground, these positions have the same sign. Because we're measuring from the ground up. We're measuring from the ground up. Now, delta y is equal to that. Initially, this ball was in the balloon, and this balloon was actually exactly 15 meters above the ground. The initial velocity was 3.4. And there was change in time. The gravitational acceleration is 9.8 meters per second squared, delta t squared. We have a quadratic equation. Now, half times the 9.8 is 4.9. Delta t squared plus 3.4 delta t minus 15 equals 0. Then we're going to use delta t, which equals minus b plus or minus the square root of b squared minus 4ac over 2a minus 3.4 plus or minus the square root. A is 4.9 and C is minus 15. Divided by 2A, which is 4.9. So you're going to get two answers out of this. Let us use a calculator to see what we have got. Okay, remember, we're just going to bring this stuff back. We're going to bring this stuff right back. Right, so what we have here. Okay, let's use a calculator. We have the square root. We square it. Okay, let's do computational. So the square root of 3.4. Can do all of it. That's what some students do. So you can do minus 3.4, do the plus, the square root of 3.4, squared minus 4 by 4.9 by negative 15 divided by 2 times 4.9. Right, and then you're getting 1.43676, which is about 1.44. 1.44 seconds, and we know that delta t is not equal to the other one. So you can also do here we can put here a negative, which is minus 2.13. So it's not that one. It's not that one. It's not that one. It's not that one. Right, we found the T1. So you can then say, therefore, the T1 is 1.44 seconds. 1.44 seconds. 1.44 seconds. Then now, the height of the hot air balloon above the ground at the instant when the ball struck the ground. The height of the hot air balloon above the ground at the instant when the ball struck the ground. You have 4 marks. And you have 4 minutes. 4 marks, you have 4 minutes. Four marks, you have 4 minutes. Right. Okay, good. Let me show the story, please. Right, here's the story. And in this story, we're reading about a hot air balloon moves vertically downwards. So here's the hot air balloon that is moving vertically downwards at a constant velocity of 3.4 meters per second. Okay, it's moving downwards at a constant velocity of 3.4 meters per second when the balloon is 15 meters above the ground. It is 15 meters above the ground, yeah? At the instant that it is 15 meters above the ground, you will just possibly find the hot air balloon on Friday. Above the ground, a small ball is dropped. Possibly instead of going down, then the hot air balloon is going to be going up on Friday. So when the balloon is 15 meters above the ground, a small ball is dropped from the balloon. Here is the little ball. It's dropped, so it's just released. It's not thrown. Refer to the diagram below. So its initial velocity, it's going to be 3.4 meters per second downwards. Okay, so if this is the case, we are asking the question. We are asking the question, what will the height of the balloon be above the ground at the instant that this stone strikes the ground? At the instant that the stone strikes the ground, what will, right, we continue. We continue. We continue. Right. Okay, 15.06. Okay, yeah, that's fine. 15.06, I'm noting that. So the height is 15 meters and the initial velocity is 3.4 meters per second downwards. And then now we're then saying what we want here. The height of the hot air balloon above the ground at the instant when the stone struck the ground. Check it out. Check it out. Right? Okay, so we're going to check Naor's answer. 15.06, the height. 15.06 meters is the height. 15.06 meters is the height. So delta y becomes VI delta t plus half a delta t squared. We noted a couple of things about this balloon. This balloon is like a muffin, however the shape. And now the ball is dropped. When this happens, would be interested in knowing by how much it will go down. Its initial velocity was so now if we decide to then say upwards is positive, so we're choosing upwards to be what? Positive. Which is minus 3.4. Okay, it's minus 3.4. We choose upwards as positive and it was going down. So if it was going down, then we agree, therefore, that it's going to be negative 3.4 meters of initial velocity. The time we got is just 1.44 seconds. Upward is positive, but this gravitational acceleration, it's what? What is the acceleration of this? Remember, it's not in free fall and the velocity is constant, so it's zero acceleration. Zero acceleration at constant velocity. Constant velocity. Time is 1.44 squared. Right, because it's not in free fall. It's a hot air balloon, so it's like an airplane. It's subject to air resistance a lot. So it's not in free fall. The air resistance is really dealing with it and it's slowing it down. It's not in free fall. Minus 3.4. We multiply by 1.44 minus 4.896. Meters. Right. We continue. Then what is the height? Okay, it would, in 1.44 seconds at constant velocity, which means there's zero acceleration, 0 meters per second squared, is going to fall minus 4.896. Because upwards is positive, it's going to be going down this much. Meaning you then have 15 minus 4.896 meters. And therefore the height is going to be 10.1 meters. So in other, if it falls this much, and we know very well, okay, the balloon was 15 meters before. It has fallen. It has fallen minus 4.896. So 15 minus that, you have 10.1 meters. 10.1 meters. So this is going to be 10.1 meters, exactly. So it will be 10.1 meters above the ground. Above the ground. Right, that's a good question. Why do we minus? Right, we minus because the total height of the hot air balloon before was 15 meters. Out of the 15, it falls down minus 4.8. It goes down minus 4.8. So it's no longer 15 meters above the ground. It was 15 meters before, but it falls down minus it falls down 4.8. 4.8. The negative just means it's downwards because we chose upwards as positive. So it falls down minus 4.8 meters. Good. If it falls down, so it's closer to the ground. So if we are to measure now, everything is relative to the ground according to this position versus time graph. So now if we measure from the ground, so it has fallen 4.8 meters. It was 15 before, but it now is closer to the ground. But how close is it to the ground? So we need to measure for the height from the ground up. And then we find, okay, it's 10.1 meters. Find 10.1 meters above the ground. So we must subtract, we must minus, because it has reduced the height. It was high above the ground, 15 meters, but it has gone down by minus 4.8, etc. And therefore it is closer to the ground now. But how close? We then say 15 minus 4.896. 15 minus 15 minus 4.896, and then we get 10.1 meters. 10.1 meters. Any question? We subtract because it has fallen. It's no longer very high. It has gone down. It has lost height. The height it has gone down by, since the time we measured the 15, it has gone down by minus 4.896. And therefore now it's closer to the ground. And then we just subtract the minus 4.896. And then we have 10.1 meters. We then have 10.1 meters. 10.1 meters. Next question. Next question. 3.4. The ball was in contact with the ground for 0.2 seconds and left the ground with a vertical upward velocity of 7.2 meters per second. Use only equations of motion to calculate the value of T3 indicated on the graph. Okay. This is yours. You try, and then we're going to discuss it. It is 15 meters above the ground. Three point 4. .4 meters. Okay. It was 15 meters and then it is falling. This velocity is constant. Constant velocity means zero acceleration. Zero acceleration. Yeah, just do that. Zero acceleration. Right. We're just practicing, please. We're just practicing. No rush. No rush. No rush. We're not running. Please don't break your fingers. Don't break your fingers. Okay, I can see 0.73. Sounds right. All right. Believing that T3 is 0.73, but let's just check. V final is V initial plus A delta T. And so now at this point, we are told that the ball was in contact with the ground for 0.2 seconds and left the ground with a vertical velocity of this. So if we choose upwards as positive, yeah, if you choose upwards as positive, right, right. So the ball was in contact with the ground for 0.2 seconds and left the ground with a vertical upward velocity of 7.2 meters per second. So it left the ground here, 7.2 meters per second. But when it left the ground, at this point, it reached the maximum height. It reached the maximum height. So at the maximum height, there's zero velocity. Initial velocity, when it leaves the ground, it goes upwards. We choose upward as positive, and this is going to be 7.2. That is positive. Gravitational acceleration is downwards all the time, but always downwards, making it negative 9.8 because it's in free fall after bouncing off the ground. And then we have delta T. The delta T is minus 7.2 divided by minus 9.8. So we have the following. $7.2. Which is 0.734. 0.73. 0.73 seconds. Zero point 0.73 seconds. So yes, you're right. Yes, you're right, because then you can then say, therefore T3 on the graph is 0.73 seconds. 0.73 seconds. Let's move to the next question. A battery of EMF 12 volts and internal resistance of 0.2 ohms is connected to three resistors, a high resistance voltmeter, right, and two switches, an ammeter and connecting wires of negligible resistance as shown in the circuit diagram below. The three resistors have different unknown resistances, right? So these have different unknown resistances. There's Rx, there's Ry, there's Rz. The resistance of Ry is twice the resistance of Rx. When both switches are closed, switch 1, switch 2, but both of them are closed, the reading on the ammeter is 5.5 amperes. 5.5 amperes. 5.5 amperes. Right. Give a reason why there's no current through resistor RZ. Give a reason why there's no current through resistor RZ. Easy. Hey, this question is popular. Very nice question. It's a practice session for us. We're doing 8.1. What do you think the answer is to 8.1? Right. Did you do the rest of this question? You already are. You're saying, can you do the next question? Because we have already done this one. Okay, good. That's fine. So I'll then say the resistor, right, the resistor RZ is short-circuited. Is short-circuited. If you don't want to say that, the current follows the path of least resistance. Follows the path of least resistance. Calculate the resistance of resistor Ry. Okay, because there's least resistance. The resistance is very small. The resistance is so much here, so the current is going to branch this way instead of branching that way. That's why there's no current flowing through that. Let us calculate the resistance of resistor Ry. Right. Let us calculate the resistance of resistor Ry. You have 5 minutes, 5 marks. Five minutes, 5 marks. We need the resistance of resistor Ry. The resistance of resistor Ry. We need the resistance of resistor Ry. It's going to be there, this one, on Friday. Let's see what you can do there. Okay, let's just do corrections quickly. Let's just do corrections quickly. Right, because Rx and Ry are parallel to each other, so we're going to say 1 over R parallel is 1 over Rx plus 1 over Ry, because these are parallel to each other. These are parallel to each other. But resistance, the resistance of Ry is twice the resistance of Rx. So if the resistance of Ry is twice the resistance of Rx, okay, good, let me give you a chance. Good, let me give you a chance. Let me give you some more minutes. Please let us know when you're done. Because we're just practicing. I want to see what you think about the questions, then you can do the corrections. But trying the questions will allow you to understand more. Because you will see where you made some mistakes, so that on Friday you avoid the same mistakes. You'll see that, okay, but here I made a mistake, and therefore on Friday I must not repeat the same mistake. So that is what is important. That is what is important. That is what is important. That is what becomes so important. So you let us know when you're done. Then you're going to do the corrections. Right. We continue. We continue. Right, you let us know when you're done. It's gonna be there on Friday, so already practicing. By trying the questions, you are, you know, familiarizing yourself with the questions. Familiarizing yourself with the questions. Right, you're familiarizing yourself with the questions. Right. Right. How far? How far? Right. How far? Okay. Oh, sorry. Okay, 5.92. Thank you. You then say the resistance is 5.92 ohms. And that is the resistance of resistor Y, which would mean like R sub Y. Okay, let's check if this is true or not. Let us check if this is true or not. So obviously you would have to say these two are in parallel. So that you have 1 over R parallel. It's 1 over Rx. But now, this resistance of resistor Y is twice the resistance of resistor X, so that this one is 2 times Rx. 2 times Rx. And therefore, if you add everything here, you're going to have the same as what? So it's like we're going to have the following, yeah? 1 over Rp is actually 2Rx, which is 2 plus 1. 3 over 2Rx, which is exactly the same as Rp. You invert this, which is the same as 2 out of 3, 2Rx out of 3, which is 0.67 Rx, which is 0.67 Rx. And then now we got the resistance of the parallel combination. The resistance of the parallel combination, which is exactly that one. But we know that the EMF is I external resistance plus internal resistance. The external resistance is exactly 12 volts. And then the current becomes what? right, the current becomes what we have been told. When both switches are closed and switches are closed, the reading on the ammeter is 5.5 amperes. And therefore, now we have the parallel combination has an equivalent resistance of 0.67 Rx plus a battery of EMF 12 volts and an internal resistance of 0.2 ohms. And therefore, we want to get the answer to this. 5.5. $3.685. Times 0.2. 1.1. So Rx is going to be 12 minus 1.1, you divide by 3.685, and you get the answer. $12. 1.1 divided by 3.685, which is 2.96. 2.96 ohms, right? And then at this point, we found Rx. And then we come and then say Ry is 2 times Rx, which is 2 times. Rx is 2.96. Which is times 2, which is 5.92. 5.92. We got 5.92 ohms. 5.92 ohms, and that's the answer. 5.92 ohms. 5.92 ohms. Calculate the resistance of resistor Ry is 5.92 ohms. Okay, the rest of the problems are homework. Calculate the power dissipated by resistor Rx. The power dissipated by resistor Rx is a home activity. Let me see. Let me see. Yeah, that's correct. Yes, it's correct. Your 5.92 is correct. Your 5.92 is correct as the resistance of resistor Y is correct. But now, yeah. Good, let's do the homework. The power dissipated by the resistor Rx is a home activity. It's a home activity. It's a home activity. The participate by resistor Rx is a home activity. Yeah, that is your only home activity. Just try the participate by resistor Rx. Your home activity does not give a lot. We'll see you tomorrow at 4 p.m. Yeah, but you can send your answer to 8.3. And then, obviously, tomorrow, yeah, the other papers we're going to try is not only this paper, but the other papers that are going to be tried. But thanks for joining us today. Until tomorrow, take care and have a good evening and goodbye. Goodbye now.